Great. Let's see if I can sort this out. So dark. Okay. Sorry. Hit a roadblock. Oh. Okay, so everyone got my email, I hope, because if you didn't, you gotta figure that out, how you're, I contacted you through Moodle, so I'm assuming that you get those messages. They're really annoying and kind of the main reason why I wanted to move to Slack, but it has to go out as this bulk email. Anyways, if you didn't get an email from me yesterday, I don't know what to do. Hopefully you did. So your assignment, right, is due today technically, right? But I postponed it till Monday. If you hand it in now, you get 1 bonus mark, rewarding instead of penalizing. But if you need until Monday, that's fine. You can have it until Monday. No penalty, just no bonus mark. Okay? So, great. All right. Throwing it out there. Is Avneet Brar here or Mark Carson? No, I think they're going to be MIA for a while, which means I have to lug these around for a while. Great. Does anyone not have a formula sheet? Everyone has a formula sheet? The one? We'll be using these today, the tables. All right. So here we go. Did everyone have a good long weekend? Glad to hear it. Me too. Oh, is anyone kind of late to the party here and doesn't have assignment 2 yet? Just grab it later, okay? If that's the case. Uh-oh. How do I go back to? Okay. Phew. Okay. So if you have assignment, or if you don't have assignment 2 yet, you better grab one. Have it done for Monday. Let's do a little bit of review. It feels like forever ago. So, some review. We started talking about the normal distribution, right? How do we deal with the normal distribution? Why do we even care about the normal distribution? Right, we said we use the normal distribution to figure out probabilities associated with some outcome or event. Okay. So review of the normal distribution. Let's just do a run through of the facts. Right? So these are just facts that I expect you to know and be comfortable with, right? And be able to use and apply. That's a big deal, okay? But first we'll say we use, actually this is kind of a big one. I'm not gonna put it in brackets. What was I thinking? Point number 1. We use the normal distribution normal distribution and areas under the curve, and areas under the curve to find probabilities. So then we said, okay, well, the total area under the curve, if we're talking probabilities, right, we're talking about all possible outcomes. And so the total area under the curve is 1. Right. So total area under the curve is 1. Some buzzing. Okay. And we're also going to use the fact that the normal distribution, right, it's symmetric about the mean. So first we'll say that it's centered on the mean. That's a fact. Okay. So it's centered on the, let's say the population mean, just to be extra careful. Centered on the population mean, right? Because now I'm expecting you to keep track of population sample mean, right? Or the population and the sample standard deviation, right? You have to keep those straight in your head. Okay, so it's centered on the population mean, and it's symmetric about the mean. Okay. Then we went on to say, okay, well, we can approximate areas under the curve, and today we're going to build on that and get a little bit more specific than just these rough approximations, right? We use the 68, 95, 99.7 rule to approximate areas under the curves, just to get a quick estimate. Or we can use the 68, 95, 99.7 rule. It's also called the empirical rule, but I'll never call it that. But if you have to Google it, maybe although 68, 95, 99.7 rule has a nice ring to it, and it should come up with lots of stuff. So we can use the 68, 95, 99.7 rule to approximate probabilities. Approximate probabilities. Probabilities, remember, are areas under the curve. Areas under the curve. Great. And then we said just briefly that in general, we're going to think of anything that's more than 2 standard deviations away from the mean as extreme, right? Because we said the whole goal of this is to figure out, do we have an extreme value or do we not have an extreme value? So just as a rough guideline, anything beyond 2 standard deviations from the mean, right, is going to be considered extreme. Okay. So any observation beyond 2 standard deviations from the mean will be considered extreme. we can tie it back, right, to the 68, 95, 99.7 rule. 68, 1 standard deviation away from the mean. 2 standard deviations, we have the central 95%, right? And so 2 standard deviations, basically what we're saying is, if you're not in the central 95%, right, the most common 95%, then you're extreme, right? So you're in either tail. Okay. So we have something like this, right? A normal distribution. Let's see if I can, ooh. Centered on the mean. Right? And then we move out 1 sigma, 2 sigma. So mu minus 2 sigma here. 1 sigma, 2 sigma. Mu plus 2 sigma. Right. These are just points that are 2 standard deviations away from the mean. These points or observations are 2 standard deviations away from the mean. Right. So really what we're saying, right, is we have our central kind of 95% here from the 68, 95, 99.7 rule. So here everyone is kind of the same, whatever. We've got variation, but nothing unexpected, right? And then here in the tails, once we move out into the tails, that's where we have these extreme values. So extreme values are going to happen in the tails. Okay. So I'll do a little color change here. So this we're calling extreme. We're going to get more specific, but just as a rough guideline, if you're not in the central 95%, you're most likely extreme in either direction. If we think about maybe the weights of manatees, do you guys know what a manatee is? If not, you will. Manatees are sea cows. So anyways, I really like them. But so we talk about weights of manatees, right? And so we have the central 95%. I don't know what's reasonable, but should I know? Yeah, probably, but I don't. Let's say, I don't know, 500 pounds within some reason. But then you come across this little tiny guy, right? And you think, whoa, that's pretty extreme. He's so small, right? So we have this kind of intuition already saying, whoa, that's a really small manatee, right? An adult manatee that size, that's weird, right? Or, whoa, that's a huge manatee, right? On the other end of the spectrum, right? Most likely those observations are out there in the tails already, right? So we already know this intuitively, right? We see these things and we say, whoa, that's not what I was expecting, right? What you're expecting is in the central 95%-ish. And then if you see weird stuff going on, they're out in the tails. Right? So that's what we're going to be dealing with. Okay? But just as a general rule, anything that's more than 2 standard deviations away from the mean in either direction, right? You can have a really small manatee or a really big manatee, right? Both would be extreme. Okay. So the tails, so extreme values will happen in the tails of our normal distribution. So then we said, okay, well, how do I know if something is more than 2 standard deviations away from the mean, right? So then we developed the Z-score calculations, right? So the Z-score tells us how many standard deviations something is from the mean, right? It's a calculation that we do to just boil it down to a standardized scale. Okay. So to calculate how many standard deviations an observation, that observation, we're going to denote it by x. Okay. So to calculate how many standard deviations an observation x is from the mean, we find the Z-score. And we developed it last day and we said, okay, well, if Z has to be, well, it has to be the distance between the observation and the mean, and then divided by the standard deviation, right? To see how many of those standard deviations we can fit in that distance, right? So we said that x minus mu over sigma. And that's on your formula sheet in section 3.1. Right, so Z is a standardized value that tells us how many standard deviations things are from the mean. So Z is a standardized value that tells us how many standard deviations we are from the mean. So we said, okay, if we're more than 2 standard deviations away from the mean, then we'll be considered extreme, right? So that's going to translate to a Z-score that's greater than 2, right? Plus or minus 2, because we can move into either tail, right? Is going to be considered extreme, most likely. Okay. This means a Z-score larger than plus or minus 2. So further out into, or yeah. I'd like to throw the absolute value in there, but I won't. But if you remember what the absolute value is, then it might make more sense. We drop the negative. Okay. But just think, larger than 2, meaning more negative than -2 or more positive than +2. Okay. So this means that a Z-score larger than 2 will be considered extreme. I throw quotes around the extreme because I don't think that we see it in textbooks that often, but I like it as a way of saying, whoa, that's extreme, right? So it's more of a me term than a stats term. Although I think everyone would agree it's extreme. Okay. So we briefly talked about some ZScore facts, right? So Z-scores we're taking from a normal distribution, any normal distribution, and then we're shrinking it down to a standardized distribution. So it makes sense that the Z-scores are still going to follow a normal distribution. But if you think about how far is the mean from the mean, 0 standard deviations away, right? And so it's going to be centered on 0 now. Okay. And then a value that's 1 standard deviation away from the mean, right? That's going to convert to a Z of 1, right? 1, -1, 2, -2, 3, -3, and then that's basically it, right? We talked about we can only really fit 3 standard deviations under the curve before it gets too small. Okay? So some Z-score facts. Z follows a normal distribution. Z has a mean of 0. And Z has a standard deviation of 1. Okay. So the Z curve is always going to look like this. Normal distribution centered on 0 with, I'll just put sigma equal to 1, just kind of, it doesn't go anywhere, right? We could show it if we wanted to. Here at 1, 2, 3, -1, -2, -3. Right. So that's what Z is going to look like. So that's kind of a mix of review and a little sprinkling of new stuff, right? We talked more about the extreme values today, but I'll say that's the end of the review. Okay. And so now, kind of a long review, but it's been a while, so it's okay. So today we're going to develop some notation, right? So when I say Z follows a normal distribution with a mean of 0 and a standard deviation of 1, that's a lot of words that we would have to write out every time. And what you'll find is that all section 3 or chapter 3 questions are basically going to be laid out the same way. The weight of manatees follows a normal distribution with a mean of 400 and a standard deviation of 30, something like that. Right, so it's always going to have that kind of something follows a normal distribution with a mean of this and a standard deviation of this, right? And then we have to calculate probabilities using that, okay? But we use notation in place of something follows, or let's start with Z. Z follows a normal distribution with a mean of 0 and a standard deviation of 1, right? Instead of having to write that out every time, what we say is we say Z tilde or follows a capital N for normal distribution. Okay. We only deal with the normal distribution really, but I mean, if you keep going in stats, then there's lots of other distributions and they follow the same kind of setup, right? N for normal distribution, binomial for binomial distribution, etc. Normal distribution and then bracket, 0, 1, end bracket. So Z here, we're saying follows a normal distribution with a mean of 0 and a standard deviation of 1. Or in general, any x, so any observation that we pick, say manatees, right? So any manatee that we pick comes from a normal distribution, right? So x is still that observation that we're talking about, right? Where did it come from? So x follows a normal distribution with a mean mu and a standard deviation sigma. So we read this, x follows a normal distribution with a mean mu and standard deviation sigma. So that's some notation that we need to kind of get a handle on. There's no calculation there, right? It's just shorthand notation, right? So what I don't want to see is you trying to plug in some value for n, for example, because the n, remember, just represents a normal distribution, right? It's saying, here's the distribution, right? So what do we notice here? Shape, center, spread. Right. Shape, center, spread. Hey, that sounds familiar, right? Those are the three things that we need to describe a distribution completely. Right? We need to know the shape, we need to know the center, and we need to know the spread. So this little tiny notation, right? That's all we need to fully describe a distribution, a normal distribution. Cool. Any questions about that? So let's get back to a little example. And I had one, kind of a fun one. Maybe it wasn't using this one. So we'll write out the example and then we can talk about it. Okay? So the weight of a chip bag follows a normal distribution with a mean of 28.12 grams and a standard deviation of 1.5 grams. Okay? So, example, the weight of a chip bag follows a normal distribution with a mean of 28.12 grams and a standard deviation of 1.5 grams. So I think this is one of those snack size, knowing me, probably Doritos bags. Yeah. So just a little bag, right? And so even though it says 28 grams on it, or whatever, 30, right? Then we know intuitively that not every single bag weighs the exact same amount, right? We know that. We go to the vending machine and it says it weighs some amount, and we're expecting it to be roughly that amount, right? Within reason. But we would also know if we bought one and then we pick it up and it's empty or really light, right? Then we say, whoa, that's not right, right? And so that would be an extreme value, right? And so now we're just saying, okay, well, these weights actually follow a normal distribution, which they would, okay? Centered on 28.12 with a standard deviation of 1.5. Okay. So, or we could say, or the weights follow a normal distribution with a mean of 28.12 and a standard deviation of 1.5. That's way shorter. Okay. So that notation just says the exact same thing. Okay. What if I asked you, question, what's the probability of a bag weighing more than 32 grams? Okay. So what is the probability of a bag weighing more than 32 grams? Okay. So we know, okay, well, we have the 68, 95, 99.7 rule. That's all we've got so far as finding probabilities and approximating probabilities, right? But that means we have to know how many standard deviations 32 is, right? That's our observation that we're interested in. How many standard deviations is 32 from 28.12, right? And so to find this, first we have to bring it down to a Z-score, right? And then we'll know how many standard deviations 32 is from 28.12. So the first thing we're going to do is calculate our Z. And I want you to get in the habit of writing out the empty formula first before you start plugging stuff in. Okay? So Z is X minus mu over sigma. Right? It's on your formula sheet, but you'll know it in no time. Okay. So X is our observation, right? We want to know how far is 32 from 28.12. So 32 is our observation. 32, how far is it from 28.12? 28.12 divided by a standard deviation of 1.5. You might find it helpful if you start by drawing a little sketch of the normal distribution, right? Because I know it can be hard to keep track of which one's my x and which one's my mu, right? And so if you start and you draw out the normal distribution that you're working with, right, then it'll be easier to see which one's your observation and which one's your mean, right? Your mean is always in the center. So even before this question, we could have drawn out this curve here that I'm kind of drawing below it. You know what? If you have room, I'm going to make a little room here. If not, it can go where we were putting it, but. Paste it as an image. Okay, good enough. So here, right, before we even look at the question, right, just the blurb, the weight of a chip bag follows a normal distribution. Okay, that's the shape, so then you can draw out the shape. Whoop. With a mean of 28.12, so it's centered on 28.12. And then somewhere below it, we just write our sigma. I don't want you to get in the habit of drawing out those 3 ticks, right? Moving out 1.5, 3 times on either side. That's a lot of work that we don't need. Okay, so don't worry about that. Instead, we'll just write sigma is 1.5, somewhere kind of below it. So that's going to stay the same throughout the whole question. Okay. It's just our observation that we're interested in. That's what's going to change. So here in this question, drawing the exact same thing, or if you already have it, that's great. Normal distribution centered on 28.12 with a sigma of 1.5. And then the question, what's the probability of a bag weighing more than 32 grams? So we have to think of this axis here is just a number line, right? Less than 28.12 goes down here, greater than 28.12 goes up above the mean, right? And so 32, we can just draw it anywhere. It doesn't matter where, because we have no scale on there, right? The goal is to just visualize what's going on, right? So 32, I put it kind of nicely there where it's easy to see. Okay. And then I'm going to shade in the area that I want to find eventually, right? Or approximate in our case. Okay. So what's the probability of a bag weighing more than 32 grams? So everything that's weighing more, that's this area here. Okay. So I'll just put a little question mark there, right? Because that's what we want to find. So we want to try to figure out what is that area in the tail, because that's the probability. Okay. So now, okay, we know our first step. After we map it out, I should have mapped it out first. Sorry, guys. With these little ones, it's easy to get carried away, but it's our first time, so gotta be careful. But now we can calculate our Z-score, right, to see how many standard deviations 32 is from 28.12. So we can keep going with our calculation. So first do the top, the numerator. I will assume that you know the difference between the numerator and the denominator. Can't remember, which I always had kind of a hard time with until I decided that the numerator, that's numero uno, so it goes on top. And then who cares about the denominator? It goes on the bottom. So I do expect you to kind of know that terminology. Okay, so we'll deal with the numerator first. That's 32 minus 28.12. So I get 3.88 divided by 1.5. Right. So dividing by 1.5, I get 2.586, 6 repeating. So 32, now we know, is 2.586 repeating standard deviations away from the mean or above the mean. Okay. Whenever you're rounding, I would love to see some squiggly equals, approximately equal to, right? And we're going to round to 3 decimal places. So 2.587. Round to 3 decimal places. So now we know a bag weighing 32 grams is 2.587 standard deviations above the mean. Right, now we know how far it is from the mean. Would you say that's extreme? Yeah, right? Because it's more than 2 standard deviations away, right? So right away, we know that this is considered an extreme value. So we know this would be considered an extreme value. But what we want to do is we want to attach some sort of probability, right? If you saw a huge manatee and you said, whoa, that's extreme, and then you'd want to be able to back it up. And so this is where stats kind of makes its money, right? Is you want to be able to say, not just say, whoa, that's extreme. You want to be able to say that the probability of seeing something larger than that is 0.00001, for example, right? So we attach probabilities to these claims. Okay? So we need to attach probabilities, attach a probability to the claim that this is extreme. Right? That's how it's going to go. The question is asking, what is the probability? Right? But in general, if we want to say that something is extreme, right, we have to be able to prove it. And that's what stats is all about, just attaching probabilities to these unlikely events. Okay. And so, okay, we have a Z-score, a Z of 2.587. Okay. So we know the distribution of Z. Z follows a normal distribution, centered on 0, right, and a standard deviation of 1. So we calculated a value of 2.587. So we can put that somewhere here. 2.587. There is no difference, except for my wonky lines, I guess. Things got a little weird there. Doesn't matter. There is no difference between this curve and this curve, right? Because 28.12 is 0 standard deviations away from the mean, and 32 is 2.587 standard deviations away from the mean, right? So this is just a standardized version of the original curve. So it doesn't matter which one you draw, okay? But this area will be the same. Yeah. Mm-hmm. Because as a fact, Z has a standard deviation of 1 because we boiled it down to have a standard deviation of 1. Yeah, but that's good. Okay. So because these are the same, we're still looking for this area, right? Just like we were looking for that same area on the original distribution. Okay. We did this last day, but it was a while ago. Okay. So, and we're gonna have an easier way to do it after today, but we'll do it the hard way and then I'll show you the easy way. That's always a good way to do it. Hard and then easy. Okay. So 2.587, well, all we have to find probabilities, right, or areas under the curve is the 68, 95, 99.7 rule. 1 standard deviation, 2 standard deviations, 3 standard deviations, right? And so I'll just draw those in kind of a different color here. Yeah, maybe green's good. Right, we said 1 standard deviation, that's 1. Because remember, Z has a standard deviation of 1 now, right? So talking about how many standard deviations, we can just talk about -1, 1. That's 1 standard deviation away from the mean, right? -2, 2. That's 2 standard deviations away from the mean. Right. -3, 3. That's 3 standard deviations away from the mean. Say that again. Yeah. Do you mean which one are you referring to?
Like in the beginning, it would still equal out to.
Exactly. Yeah. So we've just taken our 32 and boiled it down to 2.587. So they're the exact same. Yeah. We've just miniaturized our original. Have you guys seen downsizing? It's pretty interesting. Some fun ideas. Anyways, doesn't matter. You can watch it on Netflix. Okay, yeah.
So you would have let like a unit decided, like you wouldn't have to say it's 2.587 sigmas. Like you just know.
Yeah. So because that's kind of why we like to gravitate towards the Z distribution, is because now we know, okay, we can ditch the units and just talk about, because all of these are referring to how many standard deviations we are from the mean. And because sigma is 1, then it just kind of makes the units disappear. Yeah, but good call. Yeah, so that's why we like working on the Z distribution, is because we can ditch the units and we don't have to say mu minus sigma, mu minus 2 sigma, mu minus 3 sigma, because that's just -1, -2, -3, for example. Okay, so we have our point that we're interested in here, right? We want to figure out approximately what's this area. Well, it's going to be larger than this area, but smaller than this area, right? So how do we draw that, I wonder? I'll indicate them on here. And I'll say the first one is area 1 and this is area 2. How about that? Yeah. I need more room on here. We know the area we are trying to approximate, just writing it down, trying to approximate is smaller than area 1, but larger than area 2. Is smaller than 1 and larger than 2.
Wouldn't that be the other way around?
I know, I keep getting these messed up. Oh, because, yeah, so, but if we just, and that's why we want to draw it out, right? Because this is the area that we want.
Yep.
Right? It's
That's-
gonna
that's
be,
greater than 2, which is area 1, but smaller than 3.
so it's smaller than this area, right, which I'm calling area 1.
Oh, okay.
I know it's confusing because I have 2 standard deviations here, right? So 2.587, yeah, it is larger than 2 and less than 3, right? But it's going to be, this area is less than the area to the left of, or to the right of 2, and smaller than, or sorry, and larger than the area to the right of 3 standard deviations. How about this? Or since Z, and I'm going to center this because I'm going to say it's between these 2 values, right? So since Z equal to 2.587, okay, it's less than 3 but greater than 2. Okay. So that's a fact. I think we're all kind of on board, right? 2.587 has to be somewhere between 2 and 3. Okay. So the probability, or the area in the tail, must be, here's where I always get confused. Gets confusing, right? So our area, it has to be smaller than, I'm going to keep calling it 1 in a circle, right? Area 1, that's the area to the right of 2. Okay. Has to be smaller than 1, or, and then I'll just define it down here. One is the area to the right of Z equal to 2. And it has to be larger than 2 in a circle. Where 2 is the area to the right of Z equal to 3. Right? So if we have a look here, right, our 3 is actually attached to the 2, and our 2 is actually attached to the 1. But that's because of the increasing nature of our axes, right? Things are increasing, but as we're increasing and moving out into the tails, right, the area in the tail is getting smaller. So it kind of reverses. As Z gets larger, the area in the tail gets smaller. It's a little confusing, right? But we can say, okay, well, this one kind of belongs to that one, and this one kind of belongs to this one. Right? So they switch. Okay. What is the area to the right of Z equal to 2? So now we're going to find 1. So here, centered on 0, we have a normal distribution centered on 0, and we're at Z equal to 2. That's our area 1. All we have so far is that if we move out 2 standard deviations or 2 Z's on either side of the mean, right? We've captured the central, and I'm going to go decimals for this, 0.95. Probabilities are in decimals. Right? We like percentages because they're nice to look at, right? But we should be working more in decimals. Okay? So we know we've got the central 95%, which means we have 5%, right, or 0.05 split between each of the tails evenly, right? So this area is 0.05 divided by 2, which is 0.025. And so the area of 1 is 0.025, right? Splitting the leftover 0.05 between the 2 tails, right? Because again, it has to be symmetric. What if we find area 2? Same idea. We could probably have put them on the same one, but it doesn't matter. Now we're at -3 and +3, and area 2. So in the middle, we have 0.997, which means we have 0.003 split between the 2 tails. So 0.003 divided by 2 is 0.0015. So area 2 must be worth 0.0015. We can write, right? In the first one, it's the, so 0.1 minus, because the total area under the curve is 1, right? And then you take 1 minus 0.95, because that's taken up in the center. And then 1 minus 0.95 gives you the 0.05. I'll just say 1 minus 0.95. Oops, I won't put it there. Is 0.05. Right. And same thing here. 1 minus 0.997 is 0.003. Reverse order. Snuck them in there. All right, so we're just taking this, we know the area in the center, right? The 68, 95, 99.7 rule. And so we can say, okay, well, if it's on the center, then it's in the tails and it has to be split evenly. So now we can write that the area in the tail, right, or is that how we had? Yeah, is between 2 and 1. Right. I'll say here 2 and 1. Or the area in the tail is between 2.0015 and 1.025. Oof. Once we get numbers in there, right, it's easy to see that, oh, okay, well, I shouldn't say easy, because I don't know about you guys, but I don't love inequalities, right? But the one that makes an L, you read it as less than, right? Greater than, less than, greater than. So the area in the tail has to be greater than 0.0015, but less than 0.025. If we had them the other way around, it wouldn't make sense, right? There is no area that is less than 0.025, but greater than 0.0015, right? That doesn't exist. And so we have to be careful with that. Won't you be relieved to know that this is not how we'll spend our days? The 68, 95, 99.7 rule. What a relief. So I want you to look at your formula sheet, and that's why, if you don't have one, let me know. Everyone has one? Even if you don't have it with you, you can have one here. I've got extras. We have a loaner system. You left it at home. Because you'll want to have it in front of you. Yeah. You're all good? Yeah.
I'll take one.
Now that you know it's going to save your bacon, yeah, we're interested. Give us that table. Okay. So what's new this term is we're actually not going to use the first table. You have yours. I'm cutting it. So the kind of the second page in your pamphlet, it's out. You can still have a look at it, and I think you'll be able to kind of decipher what's going on there. But we're just going to go straight to the last table. Okay. So I have it on here. Let me just go back. Okay, so yeah, so table A is out. We're not going to use it. Yeah, it's got a table A.
So you can just draw the line through it.
If it gives you pleasure, yeah, do it. And that's 2 pages. Table C is going to be really important though. This is from a different textbook from a long time ago, but it doesn't matter. I still like these. So table C, that's the moneymaker for us. Okay. And so you should have table C in front of you, and it looks like this. Right?
We can get rid of table A for the term.
Yeah. It's out. Okay. So this looks kind of familiar, right? It's got T's on there that we're not familiar with yet, but we will be. Okay. And okay, so here without even, we're pretty good at guessing what's going on, right? And so here, we don't know what the confidence level is, but this looks familiar. 68, 95, 99.7%. Right, so here we have the central 95%. That's good, right? And for the very beginning, when we're just starting now, right, we're gonna ignore all of these, although they look kind of similar, right? And go down to the bottom where you have a Z star. So we are only going to be interested in these second to last two lines, okay? Z star and the one-sided P probability, right? And so the one-sided is just saying the area in one of the tails. Okay? So here we've got Z's. And how I want you to think of those is what we saw with 2 standard deviations and 3 standard deviations, right? Same idea. So our Z-score is going to fall somewhere between these values. Wait, what if we have a negative? You can just drop it, right? Because whatever happens on the upper end happens on the lower end, right? So it's going to behave the same way. And so that's why this table only has positive values. But if you calculate a negative Z, you just drop the negative, right? And try to place it on this line. So what we would do is we would try to take our 2.587, right, and try to place it, and notice these are all increasing, these Z's are increasing as we move out further and further into the tail. Okay. And so we've got increasing and 2.5, what was it, 87? So 2.587 would be somewhere between 2.576 and 2.807. That's more precise, right? Still an approximation, but it's kind of zeroed in more than between 2 and 3. But it behaves the same way. So now we're saying, okay, well, our Z is somewhere between these two values. So our area in the tail must be between, and we have to read it from right to left, right? Because as we're moving out in our Z-scores, right, we're moving out further and further into the tail. We've seen this already, right? We're moving further and out into the tails. The area in the tail gets smaller and smaller and smaller, right? So as our Z increases, the area in the tail gets smaller and smaller, right? So once you find your two values that wrap around your calculated Z, then you can go down here and say, okay, well, the area in the tail must be between 0.0025 and 0.005. That's new, that's exciting, cuts out a lot of work, right, from the 68, 95, 99.7 rule. Okay, but let's make some notes. For better approximations, oh, if you're the kind that likes to wrap examples up, that would be your answer, right? The area in the tail is between 0.0015 and 0.025. So that's kind of the end of the example. We should have written out a little blurb. And you know what? You got me, I will. You can sneak it in if you want. Therefore, the probability that a bag weighs more than 32 grams is between 0.0015 and 0.025. No, because these days, and that's what the table A, the one that we all happily crossed out, does. But for what we're trying to move towards is we should be using R to calculate these things, or any sort of software, right, to calculate these probabilities. So by hand, we just need to be able to develop approximations. Oh, now I can't remember how I started the other one. Oh well. Oh, thank you. For better approximations of the area under the curve, we use, it's called the t-table. We haven't talked about t's, but it's still called the t-table. We use the t-table, or if you're looking at your tables, table C. I mean, can't talk to anyone about table C. No one will know what you mean, but for us, it's just called table C, right? So what do we do? Using the Z star line, we find the two values that wrap around our calculated Z. We find the two values, oops, the two values, oops, that wrap around our calculated Z. Then trace down to the one-sided P, then trace down to the one-sided P, where P stands for probability, stands for probability. To find the areas in the curve or areas in the tail. To find areas in the tail. So going back to the example, right, Z we said was 2.587, I think. Ooh, long time ago. Yeah, 2.587. Okay. So what we found was that Z equal to 2.587 on our table, okay, is going to be between 2.587. It's bigger than 2.576, but it's smaller than 2.807. So I'm on the table now. So I have so. First so doesn't need to be there. So the area in the tail and you're going to write these from right to left, right, is between 0.0025 and 0.005. Okay. So you'll want to just double check that they're increasing as you move across. All right, 0.0025 is less than 0.005, so it makes sense. Okay. Compared to before, where we said that the area in the tail was between 0.0015 0.0015 and 0.025. The second one, the one that we did with the table, right, that's much more precise. Still an approximation, right? But the approximation from the table is much more precise. So in a pinch, if you don't have a table, you can use the 68, 95, 99.7 rule. If you have a table, we'll use that. Great. See you guys on Friday for the lab, if you can make it. Hmm.